All right, guys, this is going to be a quick video for single displacement reaction example problems and double displacement reaction example problems as well. So start off here with question number 3. I'm in the single displacement section of the all reactions worksheet or packet. Here we have lithium reacting with calcium sulfate. For single displacement reactions, you're going to need the activity series, which is on the back of your periodic table. We have to first look and see if this reaction is going to happen. And what we're looking for is we want our lonely metal or our unbonded metal solid to be higher up on the activity series than the metal that is in solution or bonded. So we need here lithium to be higher than calcium. Well, lithium is right here at the very top and definitely higher than calcium. So this reaction will go. Lithium will be able to overtake calcium for that spot with sulfate there. So then our next step is to make the products. And for these, it's as simple as switching your two metals. I'm going to have calcium by itself, and then lithium is going to bond to sulfate. Whenever I make an element or something by itself, I have to check to see if it's a diatomic. Calcium is not a diatomic, so I'm good to go there. Over here, whenever I make a compound, I have to check the charges and make sure they're neutral. Lithium has a charge of +1 and sulfate has a charge of -2. So I'm going to need a little 2 there to show that I need 2 lithiums. Remember, get rid of those charges after you're done because this is a neutral compound, so we don't want those hanging out. Last step here would be to do any balancing that you need to do. I have 2 lithiums on the product side, and so I need 2 on the reactant side, and then I'm good to go. If you're thinking about states of matter here, single displacement reactions are always going to be a metal solid plus an aqueous solution yields a metal solid if there's a reaction and an aqueous solution. Okay. All right, let's go on to our next one here. Number 8, I'm going to switch colors. Silver on the periodic table is Ag, and we said we're always starting with a solid for our metal. And then sometimes we might have hydrochloric acid or another acid that we'll use. Remember the naming procedure for this, since there's hydro, I'm just grabbing the root right off the periodic table. So chlor is chlorine, of course. And then I'm bonding that to however many hydrogens I need to neutralize the charge. So we have HCl here. Our second thing in a single displacement reaction is aqueous. And the next step here is to take a look at our 2 metals. Our metals here are silver, and then hydrogen is misbehaving like a metal. We need the silver or the lonely metal to be higher on the activity series than hydrogen. Silver is here, but hydrogen's up here. So this is going to be an example of a no reaction equation. And the reason why is silver is lower on the activity series than hydrogen, so it cannot take hydrogen's place. All right, do not draw products for this, or if you do go through drawing products, then cross them out at the end so that it's just no reaction there. All right, last one here. We have magnesium and copper phosphate. Magnesium, of course, is Mg. Always starting with a solid for our plain old metal. Copper bonded to PO4. Phosphate is a -3 charge. Copper here says it's a +2. So I'm going to need a little bit of each. I need 3 coppers and I need 2 phosphates. Remember, when you're making your reactants, if you make a compound, you need to check to make sure the charges are neutralized. And if you make an element like we did magnesium, you need to check to see if it's a diatomic. This, of course, is aqueous. Next up here, we have to check to see if our metals are going to be able to trade places. We need magnesium to be higher on the list than copper. So we can find magnesium here and copper all the way down here. So we will have a reaction here. Our metals are going to switch places. So I need to switch magnesium and copper. Now copper is all by itself. And magnesium is bonded to phosphate. Copper is not a diatomic, so I don't need to add a little tiny 2. magnesium has a +2 charge, and phosphate, like we said, has a -3 charge, so I need a little bit of each here. And this is going into solution. Your bonded thing is the solution. Last step here is to balance this reaction. I have 3 coppers on the left side, so I need 3 on the right. And then I have 3 magnesiums on the right side, so I need 3 magnesiums on the left side. And that's the complete balance reaction for number 9. Big thing with single displacement reactions is to check that activity series, because like we found out, some of them will be no reaction. You need the lonely metal, or the one that's all by itself, to be higher on the list than the bonded metal. All right, we're going to scoot forward to double displacement reactions here. Picked out a couple examples for us. Let me move this down. We have calcium nitrate over here with hydrochloric acid. For these reactions, it's 2 aqueous solutions coming together. And in order for a reaction to occur, we need to find that one of the products is insoluble. Okay, so I always draw a line to show that I'm going to switch my 2 metals. That's what helps me. So hydrogen is now going to bond to nitrate. And calcium is going to bond to chlorine. Now, a couple things here. When I made hydrogen bonding to nitrate, I ditched this little tiny 2 over here. Okay, you should abandon the subscripts of the reactants when you go from reactants to products. However, there's one exception to that. You notice I kept the 3 right here with NO3. That's because NO3 is a polyatomic. So you have to keep it together just like it shows up on your list. Okay? So 2 different types of subscripts there. One is for a polyatomic. Don't break those up. One was for a charge balance situation. You can get rid of those. Now I've made 2 compounds, and like I said before, whenever you make a compound, you have to check charges. Hydrogen is a +1, nitrate's a -1, so we don't need to add anything. We're good to go. Over here, calcium's a +2 and chlorine's a -1, so I'm going to need 2 chlorines. Next thing I need to do is check to see if we have produced an insoluble compound over here. Okay, so when we're looking for that, we are considering the anions, NO3 and Cl. Let's start with NO3. NO3 is listed as a soluble ionic compound, and it has no exceptions. So this is going to be soluble, which means aqueous or dissolved in solution. Cl is also on the soluble list, and the exceptions are silver, mercury, or lead. But here we have calcium, so it's not an exception. So this is also soluble or aqueous. In this reaction, we have produced no solid product. In double replacement reactions, if you take 2 aqueous solutions and you mix them together and you create 2 new aqueous solutions, nothing really changed. You have created no real new bonds. What it actually looks like is a big old bowl of H+ ions, NO3- ions, Ca+, 2+ ions, and Cl- ions. It's just a whole bunch of ions, and none of them have created any new bonds unless you make a solid. So this reaction I would cross off and I would write no reaction. You took 2 liquids, mixed them together, you still have 1 big pot of liquid, okay? No solids formed, nothing interesting happened, no reaction occurred. All right, let's do the last problem here. We have cobalt nitrate and potassium hydroxide. Cobalt is CO and nitrate is NO3. Plus potassium is K, and hydroxide is a polyatomic OH. Whenever we make compounds, we have to check charges. We have a +2 here and a -1, so I'm going to need 2 nitrates. Potassium is a +1 and hydroxide is a -1, so I'm good to go. Now, just like any other double replacement reaction, my metals are going to switch places. So potassium is going to bond to nitrate. Keep the little 3 for nitrate, but ditch that outer 2. I don't need the subscripts that were there for charges. And cobalt hydroxide here. Careful with the size of those O's. This little O goes with the C for cobalt, and the big O goes for oxygen. All right, made 2 new compounds, so I got to check charges. +1, -1, good to go there. Cobalt, it said, was a +2, and hydroxide we know is a -1, so I'm going to need 2 hydroxides here. Now let's check to see if either of these products are soluble or insoluble. NO3 is our first anion here. NO3 is always soluble, so this is going to be an aqueous compound. Soluble means dissolved in water or dissolves in water. This next one, our anion, is hydroxide or OH. That's on the insoluble list, but it has some exceptions. Alkali metal cations. Those are the metals in group 1, and cobalt is not in group 1. NH4, Ca, 2+, Sr, 2+, or Ba, 2+. Cobalt is none of those. Cobalt's a transition metal, not on that list. So that means there is no exception. Instead, it is insoluble, or going to be a solid that forms. So in this case, we do have a reaction because we formed a solid. So we mixed 2 liquids together, and all of a sudden there was a solid in the beaker or wherever we were mixing it in. Okay. So for this reaction, we leave our products because it occurred. And then the last step is to make sure that we balance the reaction, have the same amount of everything on each side. I have 2 hydroxides on the product side, so I need 2 on the reactant side. That means I need 2 potassiums on the product side, and I'm good with having 2 nitrates on both sides. So I am good to go. That is my final balance reaction. The very final thing is just to make sure you note that the reactants in a double replacement reaction are always aqueous. You don't have to check those out on the solubility table. They're always going to be dissolved. Even if it says they're not dissolvable, we can do things to manipulate them to make them dissolve, to use as reactants. Okay, that concludes single replacement and double replacement practice problems so that you can kind of see me working through them.